Hello, everybody, and welcome to this presentation. My name is Franklin Alvarez. I am a PhD candidate at the Hanover Medical School. I've been working with computational models of hearing for a while now, and this time I would like to talk about our new project of computational loudness model for electric and acoustic stimulation. As the title specifies, we are basing our predictions on the peripheral neural activity. We know that the auditory pathway contains all the stages involved in sound perception. The most peripheral part of the auditory pathway is the cochlea. Therefore, a computational model will be focused on the neural activity that occurs in the cochlear nerve. From this neural activity, we will try to predict loudness, which is a perceptual feature that is well known to be related with the cortical neural activity. Therefore, our computational model has to somehow account for the effects of all the stages in between. We also are taking into account two ways of stimulating the cochlea. The first one is through our natural mechanism in the inner ear for transducing mechanical sound waves into neural activity. And the second one is through the cochlear implant, where the auditory nerve fiber are stimulated with electrical pulses that come from an implanted electrode array in the cochlea. This mechanism of stimulation have been modeled in several works, but I would like to highlight the ones that we are using in our project. For acoustic stimulation, the Bruce-Serfani-Silani model counts with different stages to convert acoustic stimulus into spiking patterns. In the beginning, the sound waves reaching the middle ear are filtered by followed by a very phenomenological model of the basilar membrane. This model also counts with the inner hair cell and outer hair cell representation that can be adjusted to account for hearing loss. Attached to the inner hair cell, there is a synapse model, which simulates the transmission of the neurotransmitter between the hair cell and the dendrites of the auditory nerve fiber. The output of the model will be the temporal representation of the spike activity. For the electrical stimulation, we use the Yoshi model, which consists of two leaky integrate and fire circuits coupled together. Its circuits represent the electrical stimulation over the peripheral and central axon of the auditory nerve fiber, respectively. In our group, these two models were coupled together to create a single fiber model that can be electrically and acoustically stimulated. In the right figure, it is highlighted that the acoustic stimulation focuses on the synapses between the inner hair cell and the auditory nerve fiber, while the electrical stimulation focuses on the effect of the electrical pulses over the peripheral and central node of Rambier. With this single neuron model, we are able to create the peripheral auditory model for electric and acoustic stimulation, or PAMIAs for short. As shown in the figure, the electrical stimulation over the neural population is weighted by an electro-nerve interface, which contains the activating function. This activating function was previously calculated with a finite element method using a three-dimensional model of the implanted cochlea. Also, a hearing loss model controls the parameters of the inner hair cell and outer hair cell representations in the acoustic stimulation model. The spike activity that results from the neural population is resampled and grouped by cochlear places to obtain the neural excitation. The loudness model is then attached to PAMIAs. The neural excitation will be its input, which at the same time represents the neural activity at the periphery of the auditory pathway. This neural excitation is transformed into excitation density using a temporal integration model. Then a nonlinear function converts this excitation density into loudness contribution. At this stage, we assume that we are closer to the cortical neural activity. The loudness contribution from each cochlear place is summed up to obtain a one-dimensional signal called the instantaneous loudness. From the instantaneous loudness, the short-term and long-term loudness can be computed to have a perceptual feature, as shown here. Short-term loudness is related to the rapid changes in loudness perception, while the long-term loudness describes better the perception of long stimuli. We could choose a criteria to select a single loudness index for a given stimulus. In this case, it was the maximum of the short-term loudness, and then convert this index into other well-known loudness metrics, such as sounds. Our computational model is compared to other well-known loudness models shown here. All of them have a peripheral representation, an excitation to loudness transformation, and a spatial summation, and a temporal smoothing to obtain a perceptual loudness value. A version of this loudness model was used to simulate the performance of cochlear implant users. The model was capable of reproducing the loudness growth curve when increasing the stimulation level at different stimulation rates. This allowed us to define threshold and most comfortable levels and their corresponding excitation spread. The model was also adjusted to fit this level to patients' data at the German Hearing Center. Some other experiments, such as the effect of the stimulation rate in the threshold and comfortable level, the effect of electrode separation in the loudness estimation of interleaf pulse, and the effect of amplitude modulation in loudness perception, were successfully reproduced by the model. These experiments were performed by real CI users, and the data was collected from different publications, and the model's predictions were qualitatively accurate. Then, an updated version of the model was used with acoustic simulation. First, the loudness index was mapped to a value in sounds using a linear fitting. And as shown in this image, a 1 kHz tone at 40 dB SPL resulted in a loudness of almost 1 sound, which is the expected value. Similarly to the previous experiment for electrical simulation, the model was tested against the effect of tone duration in loudness perception, equal loudness contour with short noise bursts presented at different rates, and even ramped and damped stimulus. Similarly, these experiments were collected and reproduced from different publications, and results are promising. As a closing note, I would like to mention that this is still work in progress, but we managed to predict loudness using our peripheral model PAMIES. However, the parameters for both acoustic and electrical simulation are different. Therefore, we are aiming to find a common ground where the loudness model can be fitted and perform well for both stimulation cases. Now I would like to thank you and thank my colleagues, all the funding organizations, and now it's time for questions.